So this is a short video about the mean value theorem for integrals. If I have a function f from the interval ab to r that's continuous and integrable, then there exists a constant c somewhere strictly between a and b, so that this equation is satisfied. Now you've seen a very similar result before, the intermediate value theorem, and it shouldn't be a terrible surprise that the proof of this mean value theorem is very, very similar. Just for a quick sketch as to what's going on here, let's say I have a function f which looks something along those lines. What the mean value theorem is telling me is that I can replace f by a rectangle with the same base and the same area. Okay, that should be sort of reasonably clear why that's true, right? I have this rectangle here, which is sort of my lower bound rectangle going from the bottom of f. And I can imagine drawing an upper bound rectangle starting at the largest value of f. And it's clear, right? The value of the integral of f should be somewhere between the areas of the blue rectangle and the red rectangle. And by continuously adjusting the height of the rectangle from the blue one to the red one, at some point I got across the area of f itself. And that's actually basically the proof. So here are the details. Since f is a continuous function, it's in fact a uniformly continuous function. And we proved way back when we were talking about uniformly continuous functions that there exist two numbers, x min and x max, somewhere between the interval a, b, so that f of x is between f of x min and f of x max for all x in a, b. So in other words, there exists sort of a bottom of the function and a top of the function. Okay, here they are the sides of the interval. In general, they won't be. What does that tell us? Well, that tells us that f of x min is less than the average 1 over b minus a of the integral of f from a to b, which is less than f of x max. Okay, so that's true just from our bound on the integrals of f in terms of its maximum and minimum values. Now recall, the intermediate value theorem gave us something that was gave us a condition that was very similar. For all values z between f of x min and f of x max, there exists a constant c between a and b, so that f of z is equal to z, f of c is equal to z. So that's just a restatement of the intermediate value theorem. If we compare star and double star, we'll see that this thing here is playing the role of z in the condition for the intermediate value theorem, and so we get the conclusion of the intermediate value theorem to tell us that there exists some constant c between a and b, so that f of c is exactly 1 over b minus a times the integral of f from a to b, which is exactly the conclusion that we wanted. Okay, so a fairly short proof. I'm going to defer any applications of the theorem until after we've talked about derivatives and their relationship to integrals, because that somehow makes it more interesting. I will, however, point out that you really do need continuity, and there are some silly counterexamples for functions f that aren't continuous. So for example, I could take f of x to be 0 between 0 and 0.5, and 10 between 0.5 and 1, and obviously the integral of f is equal to 5, but 5 does not show up as one of the values of f. Okay, so you need continuity, and when you have continuity, you have the result. That's it. Thanks.